Welcome back for part 2 of chapter 7. So, where we left off, we talked about different kinds of fats. We talked about how the bonds between the carbons says a lot about the type of fat that we have. We're going to dive into a little bit more detail now, and we're also going to cover something called nomenclature. Nomenclature being the rules that dictate how we name certain compounds. So hopefully you've heard the terms omega-3 and omega-6. Where are those terms coming from? As I mentioned, we have an alpha end and an omega end to our fatty acids. So the alpha end is going to be the end that contains that carboxylic group, that's C double bonded to O, as well as the same C single bonded to an OH group. So we've got carboxyl end, which we also call the alpha end. And then we have the terminal end or the omega end where the methyl group is. So remember that methyl group is a carbon surrounded by hydrogens, but also bound to the next carbon in the chain. So if we are talking about naming, we have to list off a couple of things. So one really important piece of information to know is how many carbons are in that particular fatty acid. So this will help us classify something as short chain, medium chain, or long chain, depending on how many carbons it has. We also need to know how many double bonds are between the carbons. So remember, we're ignoring the double bond that exists between the carbon and oxygen at the alpha or carboxyl end. But any of these other bonds between carbons is fair game. So if there happens to be a double bond between any of those carbons, it matters to us. And as you'll recall from our previous section, monounsaturated would mean there's one double bond. Polyunsaturated would mean two or more double bonds. And if it's saturated, that means there's no double bonds between these carbons. They are fully saturated with the maximum number of hydrogens. Lastly, we will want to talk about the fact that if there are double bonds, where are those double bonds located when we look at starting counting from this omega end? So we call them omega-3 or omega-6 because if we count 1, 2, 3, 4, 5, 6 carbons from the omega end or the methyl end, and we see that there's a double bond there starting at that sixth carbon between the sixth and seventh carbon, then that would be an omega-6 fatty acid if that's the first double bond that we find. If, however, we're counting from the methyl end and we go 1, 2, 3 carbons in, and it's between that third and fourth carbon that we find the first double bond, well, then in that case, it's going to be an omega-3 fatty acid. Now, as I mentioned, structure equals function. So omega-6 fatty acids act differently in the body than omega-3 fatty acids do. We need both of them. Both of them are very important. However, omega-3 is going to have more anti-inflammatory effects, and omega-6 is going to have more pro-inflammatory effects. Now, chronic inflammation is problematic, but we do need to have the capacity for inflammation. If we're fighting an acute illness, it's important for our body to be able to mount a response. A lot of that is pro-inflammatory. Let's say, for example, somebody's sick or injured, that pro-inflammatory response is going to be really important for them. Clotting blood, all of that's going to be really important. Whereas on the day-to-day, we may not want to have our blood super thick and prone to clotting. We may not want to have our blood vessels highly constricted, right? So we need to have this balance between the appropriate amount of omega-3s and the appropriate amount of omega-6s. And that is an area of ongoing research. There's definitely a lot of information and misinformation out there about the role of various fatty acids and what they do for the body and to the body. In general, most Americans are considered to be eating more omega-6s and not enough omega-3s. So for the most part, most of us could do with a little bit more omega-3s in our diet. Now, that does not translate to go ahead and take supplements. Your book does a pretty good job of listing out the recommendations according to risk, cardiovascular risk. So a person who's already been diagnosed with cardiovascular disease has different recommendations in terms of supplementation versus somebody who does not have a diagnosed history of cardiovascular disease. So if somebody's got high blood triglycerides, they also have differing levels of recommendations versus somebody who does not have that diagnosis. The book also mentions that there are differences in terms of supervision by a physician or doctor. If you are going to be taking supplements, it's important to let your doctor know that, and also to have that be a discussion. Hopefully that is a discussion that they can at least explain the risks and benefits. There are risks. It's not that there are no risks associated with taking something like a fish oil supplement. And so those risks do need to be weighed. So for example, a person with any kind of blood clotting disorder or who is taking medications such as a blood thinner, taking omega-3 in the doses that you would find in a supplement versus just in foods, that could cause your blood to be so thin that you would actually be at risk of bleeding, unintentional bleeding. So a small GI bleed might turn into a large bleed. A small brain bleed might turn into a large brain bleed. So certainly not without risk. The other issue, and this is a bit more emerging research and not something that your book does dive into just yet, because textbooks tend to be a little bit behind the current research, but fairly recently some evidence is coming out that individuals taking fish oil supplements and omega supplements may be at higher risk for something called AFib, so atrial fibrillation, an abnormal rhythm of the heart. And interestingly, those individuals who have AFib are at higher risk of getting blood clots that could then travel to various parts of the body and become problematic, become emboli. So when in doubt, have an informed conversation with your physician. Try and look at the best evidence and determine whether or not taking a supplement is right for you. Overall, it's better if you don't have any diagnosed history to just eat foods that have omega-3s in them. That's a safer bet. The other thing is that physicians can often have different versions of supplementation that are refined and a much higher level of the active ingredient that you're looking for. So rather than just taking fish oil, you'd be taking some very refined amounts of EPA and DHA. Hopefully you've heard those terms before. If not, those are byproducts of taking in omega-3 fatty acids. Our body can convert omega-3 alpha-linolenic acid into DHA and EPA, both of which are important for human health, as well as fetal development and infantile development in terms of brain health and eye health and various other things. But we do want to make sure that that's the right thing for you as an individual. We don't want to make a blanket statement about just taking supplements and saying it's a good idea, because it's not right for everyone. So as I mentioned, we can go ahead and look at the carboxyl end. We can look at the methyl end. Again, that carboxyl end, we're calling it alpha. That methyl end, we're calling it omega, because alpha is the beginning of the Greek alphabet, and then omega is at the very end, so it's saying the end. So here's that methyl group, the omega end, and we're counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. Not a single one of them has any double bonds in there. So this one is a saturated fatty acid because there are no double bonds in between carbons. And the way that we would use that nomenclature is to not only say, carbon, but then we would say how many carbons are in there, 10. And then there are 0 double bonds. So that's where you get that colon 0 at the end of the terminology there. No double bonds. This one here, we're starting at that methyl group again. 1, 2, the third carbon has a double bond to the fourth carbon. So we would consider that an omega-3. And it is monounsaturated because there is only one double bond between carbons. Monounsaturated fatty acid C9, because there are 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. We're using the colon there to differentiate that there is one double bond, and then in parentheses, we're telling folks where to find that double bond. So we could say this is an omega-3 fatty acid, C9 colon 1 parentheses 3 tells us a lot about that molecule. Another example here, 1, 2, 3. So at that third carbon, we have a double bond. And there's the fourth carbon, fifth, sixth, in between the sixth and seventh carbon. We've got another double bond. And so going back to the beginning, because I lost track, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 carbons there. So we know that it is not monounsaturated, not saturated, but polyunsaturated because there's more than one. So polyunsaturated fatty acid, C10 because there were 10 carbons, colon 2, 2 because there are 2 double bonds, and it's an omega-3 fatty acid because of the fact that that's the first double bond that you see. So even though there's an additional double bond later, this is the first one in the chain. That changes the pathway that it can go through in the body. The body's able to take our essential fatty acids and turn them into other things. So for example, taking omega-3 fatty acids and turning them into EPA, DHA, and other downstream products. We're also able to make these cool chemical messengers out of them, things like eicosanoids, which are important for communicating with various parts of the body, almost functioning similar to hormones in the way that they either have pro-inflammatory effects or they have anti-inflammatory effects. Pro-inflammatory if it's omega-6, anti-inflammatory if it's omega-3. These are the two essential fatty acids, omega-6 and omega-3. So omega-6, linoleic acid, omega-3, linolenic with an extra N there, linolenic acid, also called alpha linolenic acid. So those have to come from the diet. We cannot make them ourselves. Our body's really good at making other sorts of fatty acids as needed and adding double bonds and adding, saturating molecules and, putting little chunks together to make the right kinds that we're looking for. But these are two that the body cannot make. We don't have the enzymes that'll put the bonds in the right place to make these two specific ones. So we're able to make a lot of saturated fatty acids. And we can elongate unsaturated fatty acids to make other kinds of omegas, things like omega-9, but we do need to get these from the diet. So using omega-3, we can make things like EPA. The big fancy name of that is eicosapentaenoic acid, easier to say EPA. And then DHA, big fancy name for that, docosahexaenoic acid, a lot easier to say DHA. So the body has limited capacity to make both of those things, both of those types of fatty acids out of linolenic acid. But it's not 100% at being able to do that. So eating some amount of preformed EPA and DHA is often a good idea. So if we want to get these foods in our diet rather than just trying to get them from supplements, ways that we can do that would be to prioritize rich sources, foods that are rich in omega-3 or omega-6. So for omega-3, I mentioned that is a little bit more deficient in the American diet. So eating more green leafy vegetables, eating more walnuts, canola has some, pumpkin seed has some, flaxseed has some. Definitely fish, especially cold water fish, is going to be a great source of the EPA and DHA. Those are those preformed downstream products of omega-3 fatty acids. And then omega-6 is a little bit more pro-inflammatory, definitely more commonly found in the American diet. So soybean oil, safflower oil, corn oil, fruits and grains also have omega-6s. It's not that omega-6 is bad for you because it's pro-inflammatory, but an excess of omega-6 and a deficiency of omega-3, that ratio between the two is what's important to look at. So eat mostly plants and fruits and, eat fruits and vegetables and grains and all those plant-based foods, but also including things like fish. That is going to be a way to try and get the correct proportion in your diet. Fats can be solid at room temperature if they are saturated. Food manufacturers a while back figured out that you can saturate unsaturated fatty acids through a process called hydrogenation. So we talked about those double bonds between carbons being vulnerable for attack. If you throw a bunch of hydrogens at the molecule, the double bond wants to go ahead and accept a hydrogen rather than just two carbons shaking hands. It would much rather have those spaces, those bonds filled with something else like a hydrogen. A hydrogen is a really good friend in that relationship, really easy to latch on. So by adding those hydrogens, we were able to change the chemical structure of a previously polyunsaturated fatty acid, or even a monounsaturated fatty acid, by making it accept some hydrogens. The downside is that we then found out that that's maybe not super great for our health. So the reason for doing it, the rationale for doing it, would be that if we can hydrogenate oils, plant-based oils tend to be cheaper than something like butter. Also, there's this understanding that, plant-based oils tend to be better for your health. So, why not have the best of both worlds, have a plant-based oil, but make it act like a saturated fat? Make it solid at room temperature. Make it so you can make pies with it, because trying to make a pie, any of you with any culinary experience, with a liquid oil is not going to work out super well. You need to be able to fold the butter into the flour. You need to be able to roller pin it out, fold it again, roller pin it out, fold it again. You're going to get these flaky little layers. It's going to be really hard to create those layers with a fat that's liquid at room temperature rather than solid. So, those are some reasons why hydrogenation made sense. The other reason being that unsaturated fatty acids, because those double bonds are vulnerable for attack, makes it more likely for that fat to become rancid more quickly. So rancidity gives the oil and the food that was made with that oil some off flavor. If you've ever eaten, a food that contains fat that's gone bad, maybe it's not going to make you sick, but it might taste really gross and rancid. So it's a way to prevent or delay rancidity by changing the chemical structure. So we make them shelf stable for longer. We improve that crunchy, delicious, buttery texture without having to use actual butter. And back in the day, we thought that was also going to be better for health. Well, now we know hydrogenated oils are not good for us. And so it is best to avoid them. Thankfully, starting in 2006, it was required that we add trans fats to the label. So now consumers can be a little bit more savvy. There are some caveats with that. So they're able to say 0 grams of trans fat as long as each serving of that food has less than half a gram per serving of trans fat. So something could have 0.49 grams of trans fat per serving, and if you eat 5 servings, you may actually be inadvertently taking in a lot more trans fat than you realize. So we do have to become pretty savvy as consumers. Look for words like hydrogenated, partially hydrogenated oils on the back. Hydrogenated presumes that every single double bond got taken up with hydrogens, and therefore the entire fatty acids in that product are all full of hydrogens now. There are no more double bonds between carbons. But when we say partially hydrogenated, and we'll look at some pictures a little bit later, that does change things a little bit, because then we have to talk about cis versus trans. So the orientation of the hydrogens around that double bond is what is causing it to be considered cis or trans. So if we were actually saturating every single double bond between these carbons, there really wouldn't be a need to differentiate between cis and trans, because all of them would be saturated, right? Every single fat there would now be a saturated fatty acid. But when we throw those hydrogens, some of those double bonds don't get saturated. Some of those double bonds remain. But we do have this change where we get hydrogen to attach either to opposite sides or to the same side. So we change the orientation around that carbon molecule, that double bond, that carbon bond in the molecule. And so if we have ones that are across from each other, we call them trans. And if we have ones that are on the same side of the carbon, we call them cis. And these trans orientations is what tends to be associated with negative health outcomes. So that's something to be watchful for. So if we were fully hydrogenating, for example, we would take away all of those double bonds and we would just have hydrogens attached everywhere. So avoiding those trans fats when possible. They are being phased out of the food supply in the United States, but there are still some sources. So look for the words partially hydrogenated on the ingredients part of the label because the actual nutrition facts panel can have up to 0.5 gram of trans fat per serving without having to disclose that. It's allowed to say 0. It rounds down. Sneaky, sneaky. Lastly, we haven't really talked about this classification of our lipids yet in much detail, but I did mention that sterols are biologically important. Thankfully, they are not an essential nutrient, so your body is able to generate its own cholesterol. This happens in the liver. The liver is responsible to make cholesterol. And then we're able to use cholesterol. That's just kind of a general structure of sterol. So you can, without seeing all of the bonds here, you can imagine that there's a carbon in each one of these corners, and then the carbons are attached to other carbons, and any bonds that are not listed as a double bond, you're going to presume that there are some hydrogens attached there to fill up the needs of that carbon because it likes to make 3 bonds. In addition to just the basic ring structure, you can start attaching other groups to these things. So cholesterol esters versus free cholesterol. You see that there's a little bit of a difference there in that this cholesterol ester is bound to a polyunsaturated fatty acid right here. So you can't see the entire polyunsaturated fatty acid, but imagine that we've got a carboxylic group, we've got a bunch of carbons, and then at the very end, we've got a methyl group there, and there's some double bonds because we know it's polyunsaturated. So a cholesterol ester is going to be bound to a polyunsaturated fatty acid. Free cholesterol, that location there is just going to be hanging out with an OH group. So why do we need cholesterol? It does a lot of different things. One of the things that cholesterol does is it embeds itself inside of cell membranes, and it can help decide how liquid or solid that cell membrane is. So living in different environments, we may have different needs according to temperature, and so adding that cholesterol there can help with the fluidity of that lipid bilayer. We've got vitamin D that is made from our cholesterol precursors, and we know that we need vitamin D, really important for being able to absorb our calcium, for example. We know that our cholesterol and sterol families make things like testosterone and estrogen, testosterone being the primary hormone of sexual development for males and estrogen for females. And then this cool thing called bile. So bile is an interesting compound. It's made both from cholesterol as well as from heme. So if you remember heme came from the breakdown of our red blood cells. So heme is that protein component found in the red blood cells that has iron in the middle of the 4 protein subunits, and heme is the portion that binds to oxygen and carries oxygen throughout the bloodstream. Well, when those red blood cells die, the heme gets broken down, and this is the way that it gets recycled, is it gets added into this thing called bile, and we use bile to emulsify fats during fat digestion so that they can appropriately be broken down by enzymes, the various different lipases in the body, whether it's lingual lipase, gastric lipase, or pancreatic lipase. We have to get that big, huge chunk of fat in a small enough piece that those enzymes can do their job. So thankfully, bile has that amphiphilic quality similar to a phospholipid, where it has positive, negative, charged areas, and then it also has some non-polar regions. So the non-polar regions like to hang out with fat, and the charged regions like to hang out with water-soluble things, charged things. Cholesterol in food used to be kind of public enemy number 1. That's how eggs got such a bad rap, because they do have a lot of dietary cholesterol in them. However, majority of our cholesterol in our blood, and when we talk about our lipoproteins, things like LDL, the majority of that is actually going to be made in the liver. So it's the liver that's making cholesterol, and it's the liver that's making the various different lipoproteins that carry fats and cholesterol and other things in the body. But the dietary cholesterol for most people does not make a big difference in what happens to their blood cholesterol. There are some exceptions. There are some hyper responders. Some individuals do respond more to dietary cholesterol. But for the most part, eating foods like eggs or shrimp that are high in cholesterol isn't necessarily going to cause you to have quote unquote high cholesterol. If you eat foods that have a lot of cholesterol, like a beef liver, yes, they do have a lot of cholesterol in them, but most of us aren't eating massive quantities of beef liver, so that shouldn't be problematic. Um, you know, Very nutrient dense foods, and they have a lot of benefits. So we don't want to throw the baby out with the bathwater, especially considering that what's really going to have an impact on cholesterol are things like saturated fats and trans fats. So it's more about dietary pattern than individual foods containing cholesterol that's really going to impact your blood cholesterol. And the reason we care about cholesterol in the blood is because it's considered a marker for cardiovascular risk, right? We don't really feel cholesterol in the body, but if we do have cholesterol depositing itself into various arteries, including the arteries that feed the heart, that provide blood to the heart, right? Then we've got cardiovascular disease. We may have coronary artery disease if it's specifically depositing within the heart muscle, and then that could lead to myocardial infarction, heart attack, that sort of thing. So that's why we care about cholesterol in the blood, but I just want to make sure that we're not demonizing dietary cholesterol because the evidence for that is pretty shaky at this point. And the majority of people don't need to worry about dietary cholesterol, but they do need to focus on saturated fat. They need to focus on trans fat, reducing those, and increasing fresh fruits, whole vegetables. Soluble fiber is an excellent option there to help us poop out or get rid of more cholesterol, more bile, and then therefore driving down cholesterol. Kind of a complicated process, but at the end of the day, eat more plant-based foods and you'll be doing all right.